Okay, hello, welcome to my taster lesson on optimization. So what is optimization? It's a method of applying differential calculus to find the maximum and minimum values of a function. So you could literally plot a graph. Let's say this is the y-axis, this is the x-axis, and let's say we have a graph coming down from the minimum, coming all the way to the maximum and down. We could literally do trial and error, find an x value here, find an x value here, until finally we get to a maximum value. That's probably a very long way of doing it. So what we're actually going to do is use our knowledge from differentiation and try and find the maximum, right? It's called optimization because it's literally about finding the best value, the best input for x, for the best value in y. And this is used as an algorithm in pharmacy, in construction, you name it. So these are some of the key results of differentiation that I expect you to know and we're going to be applying today. So I'm not going to go through it in this video, but depending on when you are watching this video, I may have already made videos covering these aspects of differentiation. So we're going to use an example because, like I said, it's an application. It's all about just practicing. So what do we have here? We have a cylindrical can with a volume of 16 centimeters cubed. And actually I like to underline the key information. It's also a cylindrical can. AQA love asking about cylinders. The can has a lid and its height is h centimeters and its radius r centimeters. We need to find the minimum surface area of metal needed to make this can. What I always recommend is drawing out the net structure when you have something like this, just to make sure we have covered every base essentially. So we have two circles, so the area for a circle is pi r squared, so I'll just write that in here. And of course we have another one, which is also pi r squared. Okay, so we can see the height. This is the rectangle is the cylindrical metal extended out. So we can see that the height is h centimeters. Now, in terms of its length, so we imagine what its length will be because we've extended it out, we've flattened it out. So the length will actually be the circumference of the circle, as you can see here. The circumference of a circle is 2 pi r. Okay. So the length of the diameter times pi. This means the area of this rectangle is 2 pi r h. So that means our total area is pi r squared and pi r squared. So we have two circles. So that's 2 pi r squared plus 2 pi r h, the area of the rectangle. And we're going to call this equation 1. Okay, so at this point, because we're trying to find the minimum surface area needed, we're going to have to, at some point, differentiate this. Problem is, we can't differentiate in respect to r, purely because there is a h here. So always, in optimization questions, there's always a way to make another equation to try and eliminate this extra letter here. So the extra letter here is h. That's being kind of annoying. So we need to find a way to make h. So at this point, we need to go back to the question and see if they've given us any other clues. Well, yeah, they have. They've told us the volume is 16 pi centimeters cubed, so I'll probably be using that for this question. So what is the area, formula for volume? Well, it's the area of a circle times the height, so pi r squared h. And we know that's equal to 16 pi, as given in the question. So in this question, we're trying to eliminate the h. So essentially, we need to make h the subject of the formula here. So all I simply need to do is divide by pi r squared. That gives us h is 16 pi over pi r squared. And actually we can simplify this more because the pi's cancel out, so 16 over r squared. And we can call this equation 2. Okay, so now we have got this, we can eliminate the h from here by essentially subbing equation 2 into equation 1. So what do we get? So now we have a is 2 pi r squared add 2 pi r, and we're going to replace the h with our new result, which is 16 over r squared. So hopefully you can see that our first step is to try and eliminate that annoying letter, which in this case is the h. Okay, expanding this, we get 2 pi r squared now the r and r cancel out. The 2 times the 16 makes 32, so that gives us 32 pi over r. And because we're going to be differentiating this, I like to make sure r is never in a denominator. So using our indices rule, we can say 2 pi r squared plus 32 pi r to the minus 1. So we're just bringing r to the same level. So now we are in a position to differentiate this. So what do we say? We say dA over dr. Okay, so this is some of the standard results you need to know. So when we're differentiating, we bring the power to the front. So 2 times 2 is 4. That's 4 pi. And we minus 1 from the power. So we're just left with r. And again, to differentiate the 32 pi r to the minus 1, we bring the power to the front. So 32 times minus 1 is minus 32 pi. And then we minus 1 from the power, so we're left with r to the minus 2. Okay, so at this point, we can actually rewrite this to get r as a denominator again, because it's just nicer looking that way. So that is the same as saying 4 pi r minus 32 pi over r squared. Okay, so that's just our indices rules, which you should have learnt about in earlier chapters. Okay, so we're looking for a minimum surface area. So if we imagine a graph, which I will quickly squeeze into here, and the surface area can take any of these values, we're looking for the minimum. And as you can see, the minimum here, the gradient is 0. And we know dA by dr, or the differential, gives us the gradient. So if the gradient's equal to 0, we can make our differential equation we've made here equal to 0. So what we're going to say is 4 pi r minus 32 pi over r squared equals 0. Okay? And now we can rearrange this and try and work out r. So that way we'll get the minimum radius needed. So I'm going to add 32 over r squared, 32 pi over r squared to one side of the equation, and leave 4 pi r on the other side. Okay, and now we can times by r squared, so we're left with 32 pi equals 4 pi r cubed. Because if you times r squared by one side of the equation, of course you have to do it to the other. I've just done that to get rid of the fraction. Okay, and now we can divide by 4 pi. So we're left with 32 divided by 4, which is 8. Pi and pi cancel out. So we're at 8 equals r, that should be a cubed, r cubed. And now we cube root 8 So we're left with r equals 2. Okay, so because r is radius, length can only be a positive value. So radius is 2. So the minimum surface area of metal needed is when the radius is 2. Obviously, the question is not asking what is the minimum radius. So we need to plug this back into our formula for area for r to get what the answer is for the minimum surface area. So I'm going to say here, when r equals 2, area equals, we've got 2 pi, and the radius is now 2, squared, add 2 pi. I'm going to use this formula up here because obviously this first one, number 1, has a h in it, and obviously we eliminated the h earlier. So that's 2 pi times 2 times by 16 over 2 squared times by 16 over 2 squared. So we got 2 times 2 squared times pi, which is 8 pi. Add 2 pi times 2 times 16, so that's then divided by 2 squared, divided by 4, so 16 divided by 4 is 4, 4 times 2 is 8, 8 times 2 is 16, so that's 16 pi. Therefore, our minimum surface area is 24 pi. And in this question, we're working with centimeters and its area, so it's centimeters squared. So we obviously need to prove that it's also a minimum. So you may have come across the second differential, and because I'm running out of space, I'm actually going to squeeze this into this little corner down here. So the second differential is taking the derivative of our first equation, which is here. So we say that's d2a over dr squared. Okay, so let's differentiate this again. So we know we've got a constant with 1r, so it just becomes 4 pi. Now we're going to differentiate that, so we bring the power to the front, so that becomes a positive 2 times 32, which is 64 pi. And we minus 1 from the power, so that's r to the minus 3. Okay, so now if we use our minimum r that we worked out earlier, which was 2, and we plug this into the second derivative, so when r equals 2, well, we get that the second derivative is this is equal to 12 pi. 12 pi is greater than 0. Therefore, we say this value is a minimum. And we have proved that it's a minimum. And we have worked out the minimum surface area as well with 24 pi r squared. So I hope this video has been useful. I think applying differentiation is probably one of the trickier parts of maths and what a lot of students struggle with, but it is just practice. And I just want to point out here that there's a few key steps. So it's all about forming 2 equations and trying eliminating it usually, and then working out the differential and making that equal to 0 to work out where the gradient is equal to 0 to find the minimum. And then we can plug that back in to our area formula to work out the minimum surface area. And to prove that it's a minimum, we work out the second differential. And if the second differential is greater than 0, we say this is a minimum point. If the second differential is less than 0, we say it's a maximum. Okay. So So for more free resources, please subscribe to the YouTube channel, like this video, and you can also visit www.jctuition.net, which is my tutoring business, where we have helped dozens of students. We have many tutors. So yeah, please do visit it out for more free resources. All right, thank you.